Hey, I'm Felix Grasniffer and I work on continuous profiling at Datadog. Today I want to show you a new feature that we've been building. It's called Profiling Timeline and it's now in public beta for Java, Go and .NET. Let's take a look. So here we have the timeline of an HTTP request that was being served by a Go application. The first two lanes have global events such as garbage collection and the stop the world events that are associated with it. And then we get a lane for every Go routine that was involved in serving this request. Below, we get a summary of all the Go routine activity, as well as the global runtime activity. And we can slice and dice this. So for example, we can click on a single Go routine and the activity summary below will update. We can also click on the flame graph here to get a breakdown of this Go routine by stack trace. And then we can go deeper by zooming in. So we can select a time range here, click the zoom button, and as you notice, it's already updated the flame graph. So we see only what was happening in this 10 millisecond range that we just selected. And we can go even deeper and zoom again. And eventually we get to the level we are at here, where we can see the individual events. So for example, here's a running event and the associated stack trace. Here's a send event where we're waiting on a channel send operation. And here's an event where we're waiting on the scheduler to schedule us. If you're excited and want to enable this feature right away, check the description below this video for information on how to get started. If you're not sure yet, let me walk you through an example of how to use this feature to optimize the latency of a request. In order to do this, we will take a look at a service that has a post/store endpoint, which receives an HTTP file upload and writes it to disk. The service also returns the SHA-1 hash of the uploaded data, which can be used for further operations against the file. This is also known as a content addressable store. Here is the HTTP handler that is implementing this. First, we create a temporary file, and then we do an io.copy of the request body into an io.multiwriter, which is copying the data to our temporary file, as well as a SHA-1 hash writer that is calculating the SHA-1 hash of the uploaded data. Once the copying is done, we take the SHA-1 hash and convert it to a hex string, which is then used to rename the file to its final location using the SHA-1 hash as the file name. We also reply with the SHA-1 hash to our client. This looks like it should be close to optimal in terms of how you would want to implement something like this. But let's take a look at the timeline feature to see how it actually performs. We're going to start our investigation in APM, where we've already selected our service. Now we're going to filter down to the endpoint we're interested in. And then we're going to look for very slow requests. Let's say those taking longer than 1 second. Now we've got a list of such requests, and we can click any one of them. And one thing we notice here is that this is particularly large store request, about 256 megabytes. So maybe this already explains why that request was slow. But let's dig in a little bit deeper. Let's click on code hotspots. Let's click timeline. And we could get started right here, but let's click open in profiling to get a full screen view to give us a little bit more screen real estate. So here we can see all the Go routines that were involved in serving this request. Let's focus in on this Go routine, which appears to be the main one, and let's see what it's doing. So about 74% of its time is spent in syscalls, and 25% of its time is spent running, as in executing Go code. So for those syscalls, I would probably expect that most of this is writing to our temporary file. But is that really the case? Let's find out. Let's go to the flame graph and see what's happening. Here we see the syscall, and if we go down a little bit, we see what it's doing. To our surprise, this is not actually writing to file. This is our os.rename operation, which we would have probably expected to be really fast. Instead, it's taking 1.4 seconds. What's going on? To understand this problem, let's take a look at how our application is writing data to disk. What's happening is that our application is using a syscall called write to copy the data to the operating system's cache. In Linux, it's called the page cache. The operating system then eventually flushes this data to the disk in the background. This already explains why the write operation was very fast and we didn't see it show up prominently in the data that we looked at. But why is the rename operation slow? A little bit of research eventually leads us to this part of the documentation of our file system. What is happening is that the rename operation essentially is triggering a flush of all our data to disk, so we have to wait for the data to actually be committed before we can proceed. This is a trade-off between durability and latency. If we wanted to get better latency, we could do the rename operation in the background using a Go routine, as shown here. This can be a good idea if we've already solved for durability by replicating our data to multiple servers from the client. So let's assume that's the case here and go with this solution. Here we have the timeline of a request that has our change applied. As we can see, the latency improved dramatically. We're down to less than 500 milliseconds from 1.8 seconds initially, and our main Go routine is now spending pretty much all of its time running. When we look at the flame graph, we see that most of this running time is going into the SHA-1 hash calculation, followed by writing to the temporary file, which is really just copying data into the operating system's cache, and then followed by reading the data off of the network connection so we can actually do stuff with it. So how can we optimize that? The problem that we're facing is that we only have a single Go routine doing all the work. Our Go routine is reading a chunk of data, hashing it, writing it to the temporary file, and then reading another chunk, hashing it, writing it to the temporary file, and so on. What we can do instead is using 3 Go routines. One Go routine reads a chunk, which is then passed on to 2 other Go routines to write the chunk to the file and hash it concurrently, while the first Go routine can already proceed to read another chunk of data from the network, which is then processed by the next loop of those other 2 Go routines. To implement this, we create our own multi-copy method, which takes an io.reader and multiple io.writers to write the data to. We're not showing all the code here, but the main loop is essentially just allocating a new 32 kilobyte buffer, reading the data into it, and then dispatching this buffer to all of our writers to write the data. When we look at the timeline of the new version of our code, we notice that we again made a very significant improvement to the latency. We're now at 326 milliseconds, whereas previously we were at 490 milliseconds. That's pretty good. On the other hand, a lot of inefficiencies have crept in. So we see that the garbage collector is kicking in a lot, and there's also a lot of stop-the-world events. The stop-the-world events are not so bad. They're only costing us maybe around 4 milliseconds for the latency of this request. But overall, wouldn't it be nice if we optimized our code further to not cause any pressure on the garbage collector? Let's see how we can do that. The problem that was causing all our garbage collections was the fact that we were allocating a new 32 kilobyte buffer for every read. So we were allocating a lot of them. The solution to that is pretty simple. We just add a new channel called free, and we use that channel to allow our writers to pass back the buffers we give to them so we can reuse them in a circle. The only thing we need to do is we need to make sure to initially fill that free channel with a few buffers that then can keep getting reused. So how does this perform? Here we have a request after our change was made, and we notice there's no more garbage collection or stop-the-world events. Well, that's great. However, the latency is now 456 milliseconds, whereas previously it was 326 milliseconds. So that's bad. Let's figure out what's going on. Let's take a look at this Go routine. In the flame graph, we can see it's doing the SHA-1 writing. And in the summary, we can see it's spending about 18% of its time unscheduled. What's going on there? Okay, to figure that out, we're going to zoom in. And it doesn't really matter where, we just want to get very close. And what we notice here is that there's all these little unscheduled events that seem to be adding up to quite a bit of time. And what's essentially happening is that we're running some Go code here, the SHA-1 hashing. Then we're done with it and we're waiting for more data. And then once that data is available, we actually spend a lot of time waiting to be scheduled by Go's scheduler. And that is problematic because, well, we would like to spend that time running already. And so we can't really change the scheduler and make this time smaller. But what we can do is we can make sure we're running for a longer period of time. The easiest way to do that is to increase our buffer size from 32 kilobytes to 1 megabyte. This will reduce the number of times our Go routine has to be scheduled by a factor of 32 and therefore eliminate a lot of these unscheduled wait times. So how well did this work? Here we have the timeline of a request after this change was made. And the first thing we notice is that our latency is now really good. We're down to 286 milliseconds, and this is probably as good as it's going to get. But let's take a look at the details. This Go routine right here, which is doing the SHA-1 hashing, is now running 99.8% of its time. So this is now really our bottleneck, and there's nothing else we can do to make this faster other than making SHA-1 hashing itself faster, which would probably be a big challenge. The other Go routine here, that's the one that's writing to the file, is spending about 50% of its time waiting for more data. That's okay too. It simply isn't as intensive to run as hashing the data that is being hashed by the SHA-1 hashing Go routine. And last but not least, this Go routine right here, that's the one that's reading the data from the network and sending the data to our writers. That one is spending 80% of its time in the receiving state as well, and that's simply waiting for the buffers being available again after the writers are done with them. There's a little bit of unscheduled time here, but there's no reason to believe that this is our bottleneck anymore, because as we can see, our Go routine doing the SHA-1 hashing is spending 285.9 milliseconds on that, and our whole request is only 286.5 milliseconds. So at this point, I think we can call this done and be happy with our optimizations. So that's it. The new timeline feature can help you with optimizing the latency of your requests, and there's no need for any additional instrumentation. Please let us know what you think in the comments, and thank you for watching.